Yes. Hello everyone, welcome to Dr. Rajesh Biogenesis Chemistry Academy, Hyderabad, Telangana State. So in this video, we are going to discuss about applications on Wagner meerwein rearrangement, advanced applications and tricky questions and shortcuts to predict the product, and some selective questions which are asked in variable entrance examinations. Okay. So already in previous video, we discussed what is a Wagner meerwein rearrangement, how carbon skeleton rearrangement will take place, and what about the attack of that particular reagent. It may be a nucleophile or it may be a base. So now we are going to discuss some more additional applications which will be most important for your examination. It is same way, some selective questions which are already asked in examination we are going to practice right now. Okay. See here. So in Wagner meerwein rearrangement there is a tendency to expand their ring size. If any choice is there for any molecule, it may readily undergo ring expansion. See, a alcoholic group is given here. Now I would like to add a proton. So then what happens? There is a dehydration will takes place on this. This is ethyl and here also ethyl. Now H2O plus. This lone pair will take this proton. They may undergo dehydration, that is loss of water molecule. Once water molecule is removed, see there is a formation of carbocation. So it may undergo ring expansion. Why? Because unstable to stable carbon skeleton rearrangement is called Wagner meerwein. Finally there is a ring expansion is observed over here. This is 4 membered. Now this is ethyl and here also ethyl and there is positive charge. Now this ethyl migrates here. Why? Because to get more stable carbocation. Secondary converted to tertiary. Now later see this is ethyl and here also ethyl and here carbocation is present. Now this is a dehydration reaction, also a elimination type of reaction. This hydrogen eliminated from here to here, and finally see you may get a double bond between these two. So here one ethyl and here also one ethyl group is present. So you can write it as 5-membered ring. This is ethyl and here one more ethyl. That is the answer. So ring expansion reactions. So most of the Wagner meerwein rearrangements are ring expansion reactions. A highly strained ring becomes a strainless free ring. Okay. So some selective reactions are there. They may also used here. See this is alcohol and 2 methyl groups are present. It is a dehydration reaction. So can I remove that hydroxy group in the form of water molecule or not? Yes, you will get a carbocation. Now this is Wagner meerwein rearrangement. This methyl migrates from here to here. Now finally see you may get a carbocation. After getting stable carbocation from adjacent carbon, we need to remove hydrogen. So remove this hydrogen and finally you may get a double bond. That is the answer. So carbon skeleton rearrangement to get unstable carbocation to stable carbocation is called Wagner meerwein rearrangement. Okay. Now see some more additional applications where you may get clarity on a terpenoids. Okay, steroidal skeleton terpenoids you will see. See this is a bicyclic compound where hydroxy group is completely orienting in below side. This is called bornyl. This is bornyl. So bornyl also represented like this. This is exactly below direction. So you can write it as dotted line. This is bornyl. And if I write a halogen atom over there, this is called bornyl chloride. In place of hydroxy I written halogen, that is called bornyl chloride. So bornyl chloride also you can represent like this. Here it is exactly below direction. This is chlorine. It is also exactly below. So this is called endo. If it is orienting over here, this is called endo alcohols. It is also completely endo. So this is called bornyl chloride. Now if I write hydroxy group above direction means it is completely in exo direction. This is called exo. So this is called isobornyl. Isobornyl. Isobornyl is represented by a thick line. Okay, so here you can write a thick line over here, means it is completely above, this is below. So you can also represent by a thick line here. And if I replace hydroxy group with a halogen, hydroxy group is simply replaced by a halogen. It is orienting above direction. This is called isobornyl chloride. So Wagner meerwein rearrangement is an excellent reaction in order to prepare most of the terpenoid skeletons. Okay, so I will show how to prepare a camphene even. Camphene is a selective hydrocarbon derivative which is prepared from Wagner meerwein rearrangement. It is also asked question in examination. See, I am taking a bornyl. So here I am taking a bornyl. This is alcoholic in nature. So if I use any acidic medium I am using, that is hydrochloric acid. Okay. Now what happens, see, there is a dehydration will takes place here. After dehydration you will get a carbocation. So remove this, simply you will get a carbocation. Now this bond breaks and attach here. Once if breaks and attaches, now here there is a bond formation will takes place and carbocation formation will takes place here. So this carbocation undergo elimination with the help of chloride ion like this, and see there is a loss of H plus, and finally see there is a formation of camphene. This is called a camphene. This is a camphene. Camphene is an unsaturated cyclic ring. Okay. So a number of structures are there for camphene. You can write in different ways. So this is a structure of camphene. So methylene, methyl, methyl, and here double bond. This is also structure of camphene. You can also write in a complete chair type of structure. See, that molecule you can also write like this. This is a 5-membered ring, and here 2 methyl groups are present here, and there is external double bond character like this. You can also write like this. Many structures are there for camphene. Okay. So it is also represented with a cyclic ring structure, methyl, and here double bond. Next, even we can also represent like this. Here there is a 2 methyl groups are present, and here 1 double bond like this. These all structures are known as camphene structures. So camphenes are prepared by using Wagner meerwein rearrangement, by using a bornyl or isobornyl. You can take any one. Finally bornyl or isobornyl get converted to camphene like this. You can take any one of the structure or general representations of camphenes. Now go through one more, that is conversion of camphene. Okay. So I am taking a camphene. See, this is a camphene, and you can also write like this. This is one more structure of camphene. So camphene on treatment with a selective acid medium, otherwise we can take hydrochloric acid. Now this proton will be added on this carbon. So after addition of this one, see, here you may get CH2 and here carbocation will be there. Now carbon skeleton rearrangement, Wagner meerwein. So after Wagner meerwein, see, this particular bond is connected to like this. Okay. Now this is initially connected here, now this is connected to this one, and here there is formation of 2 methyls, and here there is a methyl group is present already, 1 hydrogen is added, methyl, and here you will get a carbocation. Now this is added from endo direction. Why? Because above bulky groups are present. Now finally see, chlorine is attacking from below direction. This is called bornyl chloride. This is camphene, camphene to bornyl chloride. Like that we can prepare variable types of camphenes and their derivatives of camphenes, bornyls, bornyl chloride, etc. So you know camphene also represented like this, 2 methyl groups here, and this is double bond. Now what happens, say I am using hydrochloric acid. So when we use hydrochloric acid, these pi electrons are transferred on this carbon. After transferring, there will be addition of proton will takes place here. This is CH3 and this is carbocation, methyl and methyl. Now what happens, see, this methyl migrates from here to here. This is called tertiary to tertiary rearrangement, also called name-taken reaction. It is called name-taken reaction. This name-taken reaction responsible to give 2 methyl groups over here. Already 1 methyl is here, this methyl migrates here. Now this will carry positive charge. After existing positive charge here, this hydrogen migrates from here to here. It is eliminated in the form of H plus, and finally see, you may get 2 methyls here and here double bond. So if you see these 2 molecules, double bond present here, now it becomes lower side, and if you rotate this molecule here, means see, if you rotate that molecule about 180, if I rotate like this, you will get a mirror image like this. Okay, simply I am rotating, and finally these 2 methyls will come like this. This molecule you need to rotate, otherwise if you rotate in a downward direction, so finally what happens, see, there is a mirror image isomers are possible over here. Okay, so it is exactly a mirror image. Suppose see, you can also get clarity by using this. See, first you write down mirror image of this one. So here methyl, and this is methyl, and this is external double bond, and here a methylene group is separated. This is bridge, and if you rotate this molecule in a proper way, so finally you may get this kind of product. Okay, so finally we can say these two are racemic mixture, enantiomers. These two are enantiomeric in nature. These two readily used to make a racemization process. The process of converting one enantiomer to other enantiomer in presence of any acid medium is known as a racemization reaction. This is camphene racemization. Now see, I will show you some questions which are asked in examination. Okay, so what is the major product of this particular molecule when you treat with an acid medium? See, this is the one. What is the major product of this reaction? What is the major product of this molecule when you treat with a hydrochloric acid? This is called alpha pinene. When alpha pinene reacts with hydrochloric acid, alpha pinene, what will be the major product in this reaction? So can you predict the answer? See, this is a unsaturated double bond which is present within the ring. Now we know hydrochloric acid can release H plus ion. Now it will migrate over here. So why we are adding on this carbon? Why? Because if you migrate pi electron on this carbon, you will get a stable carbocation like this. Now after getting a stable carbocation, there is a bridge is present over here between 1 and 3. Now here hydrogen atom is added. Chlorine never attacks on this cation. Why? Because here there is a bridge which is suffering from strain, have a tendency to expand. This bond breaks and it will attack here. So after attacking on this carbon, here you may get methyl, and see here you will get positive charge. Now this positive charge is reacts with chloride ion, and finally see there is a formation of a chlorine which is attacks exactly from below direction, that is bornyl chloride like this. That is the answer. So this molecule many times they asked in exam. It is a carbon skeleton rearrangement. It is proceeding with Wagner meerwein rearrangement. That is the answer. Now one more. So what is the major product involved in this reaction? This is a question which is asked in IIT advanced level. Yes, go through it. What is the major product involved in this reaction? I given a carbonyl group here, and here I given a 4-membered ring, and this is H plus, and what is the product? So identify the major product involved in this reaction. Now first product, I am giving even options. This is 5-membered, and here also I given a 5-membered like this. Now option B, still 2 5-members I given. Now option C, this is 5-membered. Now here one more 5-membered is given, which is carbonyl group is adjacent to spiro. This is 5-membered. It is also 5-membered, and like this. Okay. Now carbonyl position is very closer to spiro. Carbonyl position is away from spiro. And see here you will get 2 double bonds, and here I am writing 2 double bonds. So what is the major product involved in this reaction? Okay. So can you predict the answer? Can you guess? Already a 6-membered carbonyl group is given, cyclohexanone, and there is a presence of a 4-membered ring. And if I add a proton, proton is going to be added on carbonyl group, and there is a formation of a oxonium ion 4-membered ring like this. So here this oxonium ion is highly unstable due to positive charge on high electronegative element. According to resonance rules, oxygen should not carry positive charge. Why? Because high electronegative atom gets destabilized when they carry positive charge. So there is a ring expansion will take place here, and this will be migrated here. Now these electrons are attacking here. Okay. So finally see ring expansion, 4-membered ring, 1, 2, 3, outside 3 carbons are there, 1, 2, 3, it will attack here, and this becomes hydroxy group. Okay. Remember, arrow should be written properly. You break this bond and attack here now. So after attacking, see one more time, this non-bonding electrons will accelerate this 5-membered ring. Okay. So here you are getting positive charge or not? If you break this bond, you will get a positive charge. These non-bonding electrons will migrate here. Now this bond will breaks here, it will attack here. So now you will not get a ionization over here. Why? Because it is 5-membered. 4-membered converted to 5-membered. So it is impossible to break a 5-membered ring carbon. You need to break this 6-membered ring carbon, and see here you may get this kind of reaction. This bond connected to here, and here already there is a presence of a 5-membered ring like this. Okay. Now this carbon oxygen carry a positive charge like this. Okay. Remove this proton. After removing this proton, you may get 2 5-membered rings like this. This is one 5-membered ring and this is one more. 1, 2, 3, 4, 5. And adjacent of this pyro center, you will get a carbonyl group. That is the answer. So your answer is C. Next, you can also expect one more question which is also related to Wagner meerwein rearrangement. It is also repeated many times in variable examinations. Okay, IIT Advanced as well as NEET examination, this question is repeated. Just go through it. You can easily attempt this question. So what is a major product in this reaction? So I given epoxide and here I given a 3-membered ring. Okay, so it is completely reacts with H2SO4. Okay, so what is the resultant product? This is the question which is asked in examination. Okay, so can you predict major product out of these 4 options? I am going to give some options, just you predict the answer. Okay, so this is double bond 1, 2, 3 and here there is a alcohol formation takes place. Here I am writing 1, 2, 3 and here there is a double bond formation will takes place. That is one more option which is observed in this one. Now I am writing a carbonyl group here. Next 1, 2, 3. Option D same 4-membered ring carbonyl group. Now 1, 2, 3. Now 4 options are given. Try to predict which is suitable or which is a preferred product in this reaction. Okay. So observe carefully, there is a presence of an epoxide. Epoxide is highly strained molecule and adjacent there is a strained 3-membered ring is given. Epoxide is suffering from angle strain. In the same way cyclopropane is also suffering from angle strain. So when you add a proton, which will take this proton? Proton is completely taken by strained molecule which carry a non-bonding high energy electrons. Now this lone pair will take this proton. After taking this proton, there is a formation of a oxonium ion. After getting this oxonium ion, definitely they undergo ring opening. Why? Because see, always try to open epoxy carbon such a way that you should get a stable carbocation. See, it will be open like this. If you open like this, here there is a oxygen carry neutral charge and there is a presence of a 3-membered ring like this. And see, what you will expect here? There is a positive charge. Why you open this side? Why not on this side? If you open this side, you will get a carbocation, but that carbocation is present on 3-membered ring. Okay, so if you open this side, there is a positive charge on 3-membered ring that becomes unstable, no use. So that's why we open towards above side only. Open chain should carry positive charge. And very important aspect is, if you create a positive charge outside, 3-membered sigma electrons will highly stabilize this carbocation. So this kind of cation you will get. See, this is a sigma electron carbocation, cyclopropyl methyl carbocation. Now this sigma electron is not a normal sigma electron, it is little bit bent structure is present. So the sigma electrons will stabilize this carbocation. This is more stable even as compared to benzyl. So remember, cyclopropyl methyl carbocation is more stable than benzyl. You remember this point, it is most important. Cyclopropyl methyl carbocation is more stable than benzyl. It is completely stabilized by high energy bent sigma electrons. Okay, so that's why this is highly preferred as compared to this. See, this kind of carbocation is appeared here. See, cyclopropyl adjacent carbocation is present. Now what happens? See, this kind of cations are little bit stable. At the same way, there is a choice of expanding ring, that is called Wagner meerwein rearrangement. Already one point I given that in Wagner meerwein rearrangement, definitely carbon skeleton rearrangement is observed. So when this non-bonding electrons migrates here, this bond will undergo expansion. So once if they undergo expansion, you may get like this. See, this and this, there is a bond is present. Now here you will get a double bond and here it is H. Positive charge is appeared on oxygen and here 2 bonds are connected, 1, 2. It is directly connected over here. Now remove this proton. After removing this proton, you may get this product 1, 2, 3. And here finally 1, 2, 3, 4 and see, there is a carbonyl formation. 4-membered ring, carbonyl group and carbon substitutions are adjacent to each other. Carbonyl group, carbon substitutions are adjacent to each other. That is the answer. So very important thing in this particular reaction is opening of epoxide. Which side you need to open? So don't try to open like this. See, if I take this molecule, this is oxygen, okay? And here if I open towards this side, what happens? After getting positive charge on oxygen, suppose if I open this side, okay, so here you will get OH. Now this is a 3-membered ring and here you will get positive charge, no use. See, Already it is a strain molecule. This positive charge never give additional stability of this 3-membered ring. But if you create positive charge over here, this side if you open, if you create positive charge here, there is a expansion of ring is going to be observed. That will reduce the angle strain within the molecule. Okay. So that is some examples regarding to Wagner meerwein rearrangement. Such type of advanced level reactions, repeated questions and most expected questions we will upload every day. Try to watch our videos regularly and try to like, subscribe and share your videos, and subscribe our videos and forward our videos to your friends. Say your friends, and it will be help for poor people many. And put a comment in comment section and try to put a comment such a way that it will be appreciable for your friends even. Okay, so that we will upload every way regarding to the videos, and our comment resultant answers also we are going to give in the form of answers. Okay, thank you for watching this video. Thank you for supporting us.